Hello everyone, my name is Martin and today I will be presenting this paper, Numerical Modeling of Higher-Symmetric Periodic Structures with a Hexagonal Lattice. Our goal is to study the model properties of periodic structures consisting of two metallic plates and an air gap. The structure of interest in this work is mirror half-turn symmetric as constructed in the video on the right. This higher symmetry can be obtained by first mirroring the bottom plate to create the top plate and then rotating it by 180 degrees around one of the vertices of the hexagon. In this way, we define the primitive unit cell. However, in our numerical method, we define the computational domain as a rectangular supercell. This is because the first step of the multimodal transfer matrix method, the MMTMM, is placing multimodal waveguide ports surrounding the unit cell. These ports must be aligned with the Cartesian axis as required by the CST frequency domain solver with hexahedral meshing. Open boundary conditions are then placed on the port surfaces. In this way, we compute the transfer matrix and set up and solve the periodic eigenproblem in post-processing. The way we set the periodic eigenvalue problem is with this equation, which can be resolved in three different ways depending on the part of the irreducible Brillouin zone to be investigated. The paths gamma m and mk are resolved by fixing one of the eigenvalues, thus obtaining a linear eigenvalue problem by following this paper below. For the path k gamma, neither of the eigenvalues are constant, but we may obtain the solution nevertheless by solving this polynomial eigenvalue problem. The alternative is to use the 1D MMTMM approach, where we replace two of the ports with a periodic boundary condition. First, we replace the x ports with a periodic boundary, setting the phase to 0. This allows us to resolve the gamma m path. For the other two paths, we replace the y ports with a periodic boundary, setting the phase to 0. This allows us to resolve the gamma k1 path, which contains the desired paths mk and k gamma due to the properties of the Brillouin zones. Here are the results we obtain with these approaches. On the left is the dispersion diagram, and on the right the stopband attenuation. As you can see, the results agree well with our in-house method of moments code reported in the paper below. We find that this unit cell possesses a high degree of isotropy in the stopband and is therefore equally effective to stop the propagation of the waves incident from any direction. Furthermore, the stopband bandwidth reaches almost 95%, which is larger than previously reported Hurley structures. To conclude, we have presented how to use the multimodal transfer matrix method for hexagonal lattice structures. We found that the mirror half-turn unit cell possesses an isotropic and wide-band stopband. I thank you for your attention, and for further details, I invite you to read the paper.